So, good morning. So this morning we're going to talk about something that you've been all waiting for. Application of free energy calculations to a protein ligand. I mean, in general, to host guest association. This morning I will put the emphasis on protein ligand, and I will also talk about protein-protein at the end as an extension of the protein ligand scheme that we can use. So let me give you the synopsis for this morning lecture. So I will give you some perspective. Why do we want to do this protein ligand calculations, binding free energy calculations? Then I will show you that there are two routes to achieve this goal. An alchemical route, a purely alchemical route, and a geometrical route. Then I will say a few words about relative binding free energies in the context of protein ligand. Then I will mention, just in one slide, one particular example of protein ligand free energy calculation, namely alanine scanning. And finally, I'll just touch the question of protein-protein association, which is basically beyond, going beyond protein ligand binding. So let's start with the long-standing problem of protein ligand binding. And let me start by putting it in perspective. So you have to journey back in 1987 when Peter Coleman did the first application of free energy calculations to biological problem. These were like the two science papers that I mentioned on the first day. So one was the solvation free energy, the hydration free energy of side chain analogs. And then there was also the first application of free energy calculations to in silico mutation. Okay? And so that kind of rapidly, triggered a lot of enthusiasm for free energy calculations and the use of free energy calculations to predict what hitherto was just measured experimentally. So can this calculation play a predictive role? And so at the very beginning, when in the 1990s, there were a lot of promises. I mean, pharmaceutical industry in particular was very enthusiastic about these calculations. And let's face it, I mean, the hope was that, and that's how, all the theoreticians from academia and then the people from, selling commercial software sold it. The idea was to get the results faster than by doing the experiment on the bench, wet chemistry. And it's also fair to say that these calculations did not fulfill their promises. But the idea was to, what was sold to the pharmaceutical industry was some kind of a pipeline of method. So you have a target of interest, and you have a library of drugs, and you're going through this pipeline of methods. So as you go down, you increase the sophistication of the method. So at the very beginning, up high, you have very coarse algorithms, typically shape recognition. You can really eliminate a large number of candidates just based on the shape. It just doesn't adapt to the binding pocket. As you go down, you start, you increase the sophistication of the method. So you go to rigid body docking. Then you introduce some flexibility. So typically, methods like gold, softwares like gold, like glide, FlexX if you want to introduce some flexibility. And finally, only for the few molecules, the happy few candidates that are left in the bottom, then you do this very expensive free energy calculations. But the idea of the pipeline of this so-called screening funnel, high throughput virtual screening funnel, is that at every step of the way, you have a constant computational investment. So a lot of molecules with very quick calculation, a few molecules, very long calculation. So as I said, like in the early 2000s, it was kind of an epiphany. People recognized that distances weren't that great or didn't fulfill their promises. There are two reasons for that. I think that computer cycles, not enough sampling, and also recognizing that in protein ligand problem, it's not just like calculating the binding affinity, making the molecule disappear or appear in the binding pocket. A lot can happen. I mean, this transformation can be accompanied by allosteric changes, conformational changes upon binding, which were not really amenable to MD simulations. We talked about orthogonal degrees of freedom. You can see these allosteric changes as orthogonal degrees of freedom that basically thwart or basically introduce inaccuracies in the estimation. The other main culprit, and that still remains the main culprit now that we have a lot of computer cycles to run, the force field is still the main culprit, and we're doing pretty good for proteins and for peptides and even for nucleic acids and membranes. We're not doing so great for small molecules. Let's face it, especially in the context of pairwise additive approximation. That said, as was noted by in this review paper by the Pounding group, to gauge progress toward the goal of deploying a viable engineering tool, it is essential to establish standardized benchmark sets of receptor ligand systems. This is what the community has been trying to do, I would say, in this past decade, trying to get a gold standard for doing this calculation. So this is what we're going to talk about this morning. But let me start with the theoretical underpinnings of ligand binding, protein ligand binding calculation. So what we are after here is this equilibrium. We are trying to nail down this equilibrium constant. Now you can think of tackling the problem from a pure brute force MD calculation. Actually, in the first talk of ML, you saw a movie from coming from the DE show group of a spontaneous binding of a drug, and I think it was like the beta-adrenergic receptor, which is a GPCR. If you remember the numbers, it happened over the microsecond time scale, and it was just one event. So I mean, if you are the show and you have nth on time, you can repeat that several times. But is it enough to get good statistics to access the delta G? That's kind of questionable. What you see here is something a little bit more modest that was done by the group of Jenny de Fabritis in Barcelona. And as you can see here, the binder is a small rigid molecule. And so what he did was to run brute force MD distributed on many computers, many nodes, and repeat the simulation with different starting conditions. So he did like 500 to 100 nanosecond simulations. So to get enough statistics so that he could approach, because you can envision tackling the problem from a pure brute force MD calculation, trying to access the K on and the K off, so that the rate constant for binding and for unbinding. And so the ratio of the two gives you the dissociation constant, and hence the binding fringe. It's pretty much what you're doing when you do a surface plasmon resonance or Biocore experiments, where you're actually measuring the time for the ligand to bind onto the surface, and then when you wash out the surface, how long does it take to unbind? Of course, this kind of thing can be done with a weak binder. In this case, we're talking about like -4, -5 kilocalories. If you have like a much stronger binder, even, and actually, I don't think that he saw a lot of binding events. I don't think, if you look at the PNAS paper, I don't think that he saw unbinding events. So we kind of infer based on this simulation what could be the killer. So what we want to do is something a bit more clever, maybe a better use of computer time. So let me give you the premises of the theory here. So we have a protein solvated, and it's surrounded by n ligands. We have a solution of n ligands. So we are trying to address this equilibrium, and so that's what the binding constant is. So the concentration of the complex over the concentration of the protein times the concentration of the ligand, which you can express in terms of probability that the protein, or that the ligand binds the protein, or that the ligand doesn't bind the protein. So this is the ratio of P1 over P0, which you can express now, which you can expand in terms of configuration of integrals. And I'm introducing here the notation. When I put as site subscript, means that the ligand is at the binding site. And when I put a bulk subscript, it means that the ligand lies in the bulk. So you write this for the n ligands that are in the solution, but now, by virtue of the fact that the n ligands are indiscernible, you can factorize this, and so you divide by the concentration in the ligand, so you have n over the concentration in the ligand. And you can actually introduce bulk, because the concentration, we kind of talk about an isotropic solution, homogeneous isotropic solution. So we have concentration of ligand is equal to the number of ligands divided by the bulk, by the volume of the bulk. And so finally, you end up with this relationship for the equilibrium constant. Note that I've introduced here this Dirac, just to say that either the ligand is bound to the protein, or it lies at some position x1 star, far enough from the protein that it doesn't interact with it. Okay? So as such, there isn't much we can do in terms of MD simulation with this relationship. So now this is where fringe calculations come into the picture. And I will show you now that we can take two different routes, one purely alchemical and the other purely geometrical. So let's start with the alchemical route. And this goes back, arguably, we have like three competing efforts at the time. So one effort from the Warshall group, one effort from, this is Jan Hermans, who I think was like a key actor in the field, and also the group of Andy McCallum. Let me replay this slide so that you can see the little cartoon in the lower right corner. So you can see here, I have my ligand, and I'm starting to decouple the interaction of this ligand with from the protein. And as you can see here, the ligand, as it's decoupled, moves away. This is what we call the floating ligand problem, or the wandering ligand problem. So when you try to address this thermodynamic cycle, just by considering the vertical legs, whereby you make the ligand disappear in the binding pocket. So you make the ligand disappear here on the right-hand side. You make the ligand disappear on in the bound state, and you make the ligand disappear in the unbound state. Well, if you are in the bound state and you make the ligand disappear, you basically decouple, you turn down the interaction with the protein. Then the ligand starts to float away. And so your end state is poorly defined. Not only it's poorly defined, but you will also violate thermodynamic microreversibility, because when you're trying to do the reverse transformation, then it's, well, a very unlikely event that when you erode back, it will reappear in the binding pocket of the protein. So, under these premises, what Jan Hermans thought about doing is to introduce a series of restraints that would maintain the ligand in the binding pocket. So, instead of actually imagine that you eliminate this part here. So instead of doing the classical thermodynamic cycle that you see in textbooks, which is like, the ligand, the free ligand, you transform it into nothing in the unbound state, and in the bound state, we introduce this extra step. So we introduce restraints. Because you introduce restraints in the bound state, you also have to introduce them in the unbound state. Actually, in the unbound state, you can only introduce restraints on the conformation of the ligand. So in the bound state, you freeze the conformation of the ligand, but you also freeze the position and the orientation. And since you're doing this, you're basically removing some of the configurational entropy. And this configurational entropy participates to the binding energy, so you have to calculate the contribution within this restraint. This is what's embodied in this delta G site, this delta G bulk. But on the frozen ligand, when I say frozen, it shouldn't be construed as constrained ligand, like this holonomic constraints, just like it's restrained. So we would tether the ligand in the binding pocket. So once it's restrained, then you can do the alchemical transformation. And then when you add up all these terms, then eventually you get your delta G0, which is your standard binding or absolute binding affinity. So how do we do this in practice? So it goes back to Deng and Wu and Wu and Wu, actually, 2005, for the first, like the pioneering approach. Although their approach kind of combined geometrical transformations and alchemical transformations. So the kind of assays that we are using, the ligand is, the protein ligand complex is in a box of water. We introduce groups of atoms in the protein and in the ligand to define a frame of reference, which allows us to define the orientation and the position of the ligand with respect to the protein. And then we introduce the restraints, and then we make the ligand appear or disappear. And so these different restraints correspond to configuration integrals. What you have in green are the alchemical transformations. So we have the conformational restraint, orientational restraints, the polar angles in spherical coordinates. Here we have the conformational restraint for the ligand in the bulk. In green, we have the alchemical transformation, and for the position and the orientation of the ligand, so the tumbling of the ligand in the unbound state, in the free state. So all this can be calculated analytically, and we're just talking about like a rigid body reorientation for translation. So we know what this is. It's the usual integral of r squared sine theta d theta d phi. Yeah. So that's the alchemical route. Clear so far? So now the geometrical route. But the geometrical route basically follows the same idea. We have, again, the protein, the ligand. This comes from X-ray crystallography. That's kind of a prerequisite. I mean, Ideally, you can do that with a docking solution, like take like the best pause on the docking. But this comes, in this particular case, this comes from X-ray crystallography. So we have the protein, we have the ligand. Now with freezing, we'll kind of restrain the conformation of the ligand. And so the first step is, it's kind of Russian nested dolls. So we will first apply, the first restraint will be on the conformation of the ligand in the bound state. And we will calculate the potential of mean force using the RMSD as a measure of the conformational change. So calculate that potential of mean force will tell us what's the reversible work needed to restrain the restrain the conformation of the ligand. Now, once the conformation of the ligand is frozen, then we do the orientation. So what's the free energy, what's the reversible work to maintain the ligand at a given value of the first Euler angle with the conformation frozen. Then we go to the next PMF, which will be the second Euler angle, keeping the first Euler angle and the conformation restrained. Then we go to the third Euler angle. And then we go to the first polar angle. Then we go to the second polar angle. Now everything is restrained. Now we can do the plat de resistance, like the main entry force, with the separation. So with everything frozen. So we now separate the ligand from the binding pocket. This is what you have here. Just like in the alchemical routes, we also calculate the bulk contribution as configurational integrals, like calculated analytically. The only thing that we have to be careful about is whatever restraining potential we use in the bound state, we need for consistency to do the same in the unbound state. And finally, here what you have is the potential of mean force to maintain the conformation, in the native conformation of the ligand in the bulk state. And again, that's just to balance out whatever whatever restraints you have. On the left-hand side of the thermodynamic cycle, you need to have it also on the right-hand side. Whatever you have in the bound state, you need to have in the unbound state. Yes.
So is there an assumption here that there is no change in the structure of protein once the ligand binds it?
That's a very good question. So here we are making this kind of leap of faith that in this particular description, but as we will see with the protein-protein case, where we know that upon binding there's a possibility of the protein undergoing structural changes, to actually also introduce restraints. And we also calculate the reversible work due to this restraint. That's a very good question. So to summarize, our objective was to reduce the configuration entropy. Basically, we know that upon binding, there is a significant change in the configuration of entropy, which usually is not amenable to MD brute force MD simulation. And our philosophy is, if you cannot simulate it, then restrain it, and then calculate rigorously the contribution due to this restraint. As an example here on this slide, and I'm gonna give you some numbers. We've been using, knowing that academic force field are not doing a very good job for ligands. So the purpose of this work, what we try to demonstrate is that we have the methodology to nail down protein ligand binding. And so we're just focusing on sampling issues. And so our ligand is actually a peptide. So in principle, the force field should do a good job. This is well documented experimentally. And so if you take the geometrical routes for your pretty much like 0.1 kcalmol away from the experimental value. If you take the alchemical route, you're 0.2 kcalmol from the experimental value. The bottom line here is that we're following two very different routes, and yet we're able to get the same result. So that's pretty encouraging. That we get close to experiment is also nice, but I mean, in the general case, I mean, if you have like a drug, it's very possible that you could force field in accuracies, you will not nail down exactly the experimental value. But the bottom line here is that whether you follow one route or the other, in principle, you should get the same answer. Now, what I should tell you is that the choice of one route with respect to the other is not completely without consequence. I mean, it really depends what you want to do. Depending on the kind of protein-ligand interaction, you may want to use one or the other. So imagine that what we saw the other day was in Emma's presentation. So in GPCR, it's notorious that the binding pocket is usually pretty deep in the protein. Oftentimes it looks like a socket, and so the ligand is to kind of crawl down and to find its optimal position in the binding pocket. So when the ligand is buried deep in the protein, it would be kind of ill-advised to use a PMF-based approach because then you're facing the usual autonomic degrees of freedom. Basically, all the interactions of the ligand with the protein that will kind of thwart the separation. So typically, when you have a ligand binding on the surface of the protein, the potential of Newport's approach is kind of nice. When the ligand is entered in the protein, then you may want to use energy perturbation or alchemical transformation, and then your choice of TI or FEP. An extension of this approach is due actually to the tools available in cold bars. Instead of having to define these groups of atoms, which is kind of tedious. Not only tedious, but for some ligands, it can be kind of problematic, especially when you have a long ligand, and then remember that these groups of atoms are introduced to define the orientation. So you don't want situations where you have like aligned groups of atoms. Then you have angles that are close to 180, which is never a good idea. Also, there is a possibility of so-called nimble rot, and so you're not really sampling the three orientational degrees of freedom. So we have extended the approach to the point that now you don't have to worry about introducing these three groups of atoms. We deal directly with the centers of mass of the ligand and of the protein, and using one of the nice cold bar available in the cold bar module, which is orientation. Basically, you deal with the quaternion description. And what we do then is from the quaternion, we go back to the Euler angles for the configuration of materials. But you don't have to worry about defining yourself the Euler angles and the polar angles. Okay, so another thing that I want to underscore is the starting point of this calculation. So what should you use? So of course, in ideally, you want to use the X-ray crystallographic structure, but then how do you do it? I mean, what's in practice? How do you handle this? I would say that we usually do like a minimization and equilibration, and pretty much you're ready to go. But so what we've also done is like a long equilibration, and we've averaged out the position of the ligand, so you can go over your decentralized and calculate an average position. And we saw that it makes very little difference when it comes to the estimation of the binding range. Okay, so these routes that I just showed were to get the so-called standard binding range. So you get your equilibrium constant, and your delta G0 is minus KT log of C0, 1 over 1663 angstrom square, angstrom cube, C0 K, right? You may want to consider something that's also in the textbook appears to be easier to handle, namely relative binding frequency. So in this case, imagine that you have, in this particular example, you were mutating Tamiflu into Relenza, two drugs targeting H1N1 in your mini days when you were, when what was crazy about avian flu was kind of popular to work on. So the idea here is, so you have this equilibrium for protein plus ligand A and protein plus ligand B. And so instead of calculating the standard binding ranges, we've just seen earlier, you do an alchemical transformation of ligand A into ligand B. And to complete the thermodynamic cycle, you have to do it in the bulk state and in the bound state. And so the difference in standard binding for energy is equal to the difference of the alchemical transformations. So in principle, it's easier to carry out, especially when you're dealing with congeneric series of compounds which are of interest to the pharmaceutical industry. So you usually have one scaffold and then different ornaments. So the idea here, the difference between ligand A and ligand B, is sort of change the ornament. It may require some geometric crystals in certain cases, especially when you have like weak binders. But it doesn't always work. I mean, depending on the nature of the change between the two ligands. I just want to illustrate here. So what you saw before was P41. So the P series for this particular protein that I showed in my example for standard binding ranges was the ABL kinase and binding proline-rich peptides. So like pretty rigid peptides by virtue of having like different proteins. And so you saw P41, which is one decapeptide. P5 is another decapeptide with a different, with a little bit of a different sequence. So compared to P41, we're changing 1, 2, 3, 4 amino acids. If you do if you use the geometrical route, trying to get the standard binding for energy, you get minus 5.5. The experimental value is minus 5.52, so we're doing pretty good. Now imagine that you're doing this calculation from a relative standpoint. So instead of doing this and this, you're doing the vertical transformation, turning P41 into P5 in a bulk state and in a bound state. If you do that, well, surprise, surprise, you're getting 0. If you remember the previous slides, we had minus 7.9 for the experimental value for P41, and for P5 we have minus 5.5, so that's a difference of 2.4. So we're pretty out to lunch here. So we have 0 instead of 2.4. The reason for that is that we're dealing with very large numbers. And so we have a difference of 2 large numbers. And this is prone to errors. And in fact, this result was obtained from a simulation that was 600 nanoseconds long. So twice the length of the geometric route. Actually, to compare apples and apples, that simulation, so the horizontal line was about 300 nanoseconds. That simulation, also the horizontal line, was about 300 nanoseconds. Both gave us almost the experimental binding for energy. Now, the vertical transformation, the sum of the two transformations in the bulk and in the bound state, that's also 600 nanoseconds. And that gives us 0 instead of 2.4. So in this case, what I want to emphasize here, and you're better off, it may be counterintuitive because you've heard so much that it's cheaper, it's more effective to do relative binding for energies. What we see here is that it's really prone to errors. And actually, we've doubled the time. So we've gone all the way to 1.2 microseconds, and now we're getting to 0.9. So we're still 1.5 kPa away from the experimental point. Now I want to mention alanine scanning. So you may have heard about alanine scanning. This is a common tool in the wet lab to assess the stability. So you can use alanine scanning for two purposes. You can use it in a TSA context, or TSA, thermal shift assays. So basically, by changing one amino acid into an alanine, it may destabilize the whole of your protein. And if you do the experiment, this thermal shift assay, you will see a shift in the peak corresponding of like protein like tending to fray to denature. You can also use that in the context of protein ligand or protein-protein binding by changing in the interface between the protein and the ligand, changing key residues. So just one at a time. You can see whether you destabilize the complex or maybe increase the stability of the complex. So we've introduced in VMD a tool that tool actually has a story. It was back in 2014, the fall of 2014. We were doing the usual TCBG workshop, and we had in Atlanta, Georgia Tech, and we had a few experimentalists in the audience, and they were doing this kind of thermal shift assays in as part of their routine job, and they were wondering whether this could be done also with simulation, and but they didn't want to go into the learning the fine detail of fringe calculations, and they wanted like a tool that was easy to use, almost like transparent. And so this is what we try to achieve. I don't know if we did a very good job, but so the idea here with this tool is so you enter your PDB file, your PSF file, your XSC file for the protein ligand complex, also for the protein ligand complex, and the tool will generate the assays for the alchemical transformation. So the amino acids that you will transform into alanine. So it shows a sequence, actually not shown here, but it shows a sequence of the amino acids that you want to change. So you just need to click which amino acid you want to transform into alanine, and then in the background it will run the calculation, and then you call again the plugin for the analysis, and it will show you the results. So if you go towards the blue values, then it means that the mutation, the alanine mutation, has a stabilizing effect. And if you go towards the red values, it means that the alanine change has a destabilizing effect. And the green, orange, and red dots give you like the confidence that you can have in the, or the reliability of the simulation. So if you have a red dot, it's based on the hysteresis of the forward and backward transformation. And so if you have a red dot, it's probably advisable to redo the simulation with a better sampling protocol. And if you have a green dot, in principle, you do it. So beyond protein ligand bindings, so I will finish this chapter with this consideration of. So this is a typical association problem. You have like two benzene molecules and dancing in the box of water, and you're interested in the association of the two benzene. We talked about it the other day. They can associate in a stacking motif. They can associate in a parallel displaced motif. The bottom line here is you see a lot in the literature people trying to approach the protein ligand problem or even protein-protein problem from a one-dimensional perspective. So just doing one potential unit force and applying this relationship to get the binding constant. So this is just what you have here is it implies an isotropic association by virtue of this proof factor here. And this is the potential unit force. And the bounds of the integral 0 to RC is the limit of association on the potential unit force. So this is kind of hunky-dory for small molecules like benzene, because this proof factor here basically tells you that you are under the assumption that your potential unit force is orientationally and positionally average. Right? Well, the same cannot be said for protein-protein association. And you see a plethora of papers out there where they just do the separation of the two proteins and end of story. And then they apply the Schub-Szabo formula to get the binding constant. It's not because you just don't see the tunneling of the two proteins that it doesn't exist, that it doesn't participate in the process, right? So when you have this kind of protein-protein complex, you should go for the same kind of approach that I talked about with the protein ligand, which is essentially the same framework, except that, as you mentioned, it's very likely that upon binding, the protein undergoes some conformational change. And so then the number of potentials of unit force that we have to calculate. So of course, as I mentioned before, the alchemical route is out of the question, or hinted at that, but the perturbation will be too big to make the big protein disappear in the water. So we illustrated that with a prototypical protein-protein complex bar star bindase, which binds with a delta T of minus 19 kmol. It's a pretty strong binder. It's a fast binder. Actually, if you run brute force ME in a matter of 2 to 4 microseconds, you see the binding. What you will not see is the actual canonical form, but you will see some binding. So you will see that the two proteins colliding and getting together. It's purely electrostatics. They bind by electrostatics. So I was saying that it's a little bit more complex in the sense that we need to introduce restraints on the backbone of the two proteins. So for each of them, we have a potential unit force. But in addition to that, we also need to introduce some restraints on the side chains the amino acids that are involved in the protein-protein interface. And there is a reason for that. I don't know. Go to the next slide. So the reason for that is, remember that we're using equilibrium MD, and we're doing, in our case, we were doing API for the bias exchange from sampling, but there's pretty much, thermodynamic equilibrium. And so in the process, when you separate protein 1 from protein 2, they come and go, and come and go, and come and go. And so the network of salt bridges that form the protein-protein interface, they break and reform and break and reform and break and reform. But at some point, if you do not pay attention and don't introduce restraints, these side chains, as you accrue more sampling and more sampling and more sampling, you see the wellness of the attraction potential, the potential mean force for the separation. It becomes smaller and smaller and smaller and smaller and smaller. And the reason for that is as you bring them together and separate them, bring them together and separate them, bring them together and separate, at some point they lose memory of the network of salt bridges. And so the key salt bridges that are responsible for bar-star RNA's interaction, they disappear. And they never reform. And hence you have this, which is kind of paradoxical. You sample more and you destroy the agreement. And so when we realized that we introduced some restraints on these amino acids that are part of the salt bridges, and it kind of fixes the problem. Yes?
Are we also applying a restraint in the orientation that it...
Oh, as always. Yes, as always. We have the usual 3 Euler angles. We have the 2 spherical coordinates, the phi and theta Euler angles, and then we have 2 backbone PMF, and we have 2 sidechain PMF. Yes.
So how do you reconcile these salt bridges going away over time? It's obviously
I mean,
how do you reconcile that?
how do I reconcile?
Yeah.
Well, the fact is when you do the PMF, which is like the most time-consuming PMF of all PMFs, which is the separation PMF. It's not like, people always think in terms of pulling. We're not pulling. We're separating. I mean, eventually we see them separated, but we do that at equilibrium. So they do like this, like an accordion. Just like when you do the Deccan potential of mean force, it folds, unfolds, folds, unfolds, folds, unfolds. It's the same thing. So, and in the process, you're breaking these salt bridges. And if you don't do anything special for it, then they will never reform. At some point, so when they're separated, these side chains are free to isomerize, right? And in doing so, well, when the 2 proteins come back, surprise, surprise, they don't interact anymore. And there you go. I mean, 1 salt bridge less, and you lose 2, 3, 4 kcal. Oh, and another salt bridge less, and another 2, 3, 4 kcal, and so on and so forth. And the thing is, because our simulation time is not infinite, the chance that this salt bridge, to see this salt bridge to reform, is very small. Yes?
So how do you determine the initial interface between the 2 proteins?
Well, in the case of bar-star RNAs, you have a body of work from the group of Alan First and Cambridge. So all of this is well documented. But then we use the usual, DND tools to select amino acids that are kind of common, or that are forming salt bridges between protein 1 and protein 2. It's just like a.
So is it like some kind of a docking you do initially?
No. This is crystallographic structure.
Okay.
This is a crystallographic structure. So once you have the crystallographic structure, you run your lines of TCL and to get the list of amino acids that are participating in the interface, then you know exactly who interacts with who.
Okay, in case you don't have a crystal structure, how do you?
That's a very good question. I wouldn't say it's the weakness of the method. I mean, the way we sell it is we say that it's a good method to discriminate between pauses from protein-protein docking algorithm. It's an expensive way of discriminating, but it's a way of discriminating. Yes.
I have a question about the amino interaction between the two proteins. You only mentioned that sulfur is part of the other interactions, for example, the hydrogen bond.
Yeah, when I say salt bridges, in the case of bar-style RNAs, this is essentially salt bridges, pretty electrostatic interface. But we also have like typical hydrogen bonds. We may have also hydrophobic contacts. Sure. Whatever you see that forms the interface, you should, introduce that in your series of restraints. So in our case, it's just like an ensemble of restraints on this particular amino acid, on the side chain, basically on the chi-1, chi-2, chi-3 evil angles.
If I may make a question.
Yeah.
You mentioned the hydrophobic interaction that you may have in this interface, and these simulations are done in explicit solvent. Right?
Yes.
So do you have any special treatment for the water that might be trapped in the interface or might?
In our case, not. No, in our case, well, let's face it. We haven't done that many examples. We've run, of course, bar-style RNAs quite a bit. We've run mutants of bar-style RNAs, but we've never done anything for water. But actually, this is a case where the interface is pretty dry. You have this, although it's pretty different from what David Chandler and Bruce Byrne were working on. You have this hydrophobic surfaces, and you have this so-called wetting effect. So when you bring like two hydrophobics, there's a very nice paper by David Chandler on hydrophobic effect at small and large scale. When you bring like two hydrophobic surfaces, then the water that is trapped in between, has a very high entropy, just like goes away very quickly. This is the so-called wetting effect. You have the same thing at small scales, where you have like two surfaces of hydrophobic proteins that are coming together, that are binding together. So the water that is trapped in between is just expelled very, very quickly. Okay, so with that, I kind of rest my case. And now I'm just gonna. So we have what, half an hour, 20 minutes.
10 minutes.
We have 20 minutes, so that's probably more than enough to just give you like a very quick overview of this ergodic sampling algorithm. So let me start with something that I already showed you. This typical problem that we are facing when we're doing potential mean force. So we are trying to sample alongside, but we have this in the orthogonal direction, and unbeknown to us, we didn't anticipate that, but it so happens that the choice of the reaction coordinate model that we've chosen is such that we have to deal with this orthogonal degree of freedom, and because when we're doing ABF or ABF, we have this ensemble average on the average force. It kind of implies that we are sampling, we're kind of averaging all the other degrees of freedom. So typically, at every value of psi, we want to go in that direction. ABF will help us go in that direction. At every value of psi, we're supposed to sample in in the orthogonal manifold, right? So typically, when I'm at psi 0.2, I should visit this value, but I should also visit that value. But then if the two values are separated by a high energy barrier, if I'm not doing anything about it, then I'm pretty, say like captured straight, right? So, and that kind of translates into this this kind of free energy profile, not free energy profile, sorry, histogram of the of my different bins, and I'm sure that by now you may have seen this kind of scenario, especially with the translocation of methane across water. So that's kind of pathological. It means that all my samples are piling at one end of the window. And the reason it's piling at one end of the window is so that I should replay this little cartoon that I made. It kind of means that my sampling here is kind of stuck at one end of the window, trying miserably to cross the barrier, but being unable to do so, and spending all the time doing that instead of going in that direction. Okay, so that's kind of a manifestation that my direction coordinate model was ill chosen. Right? So what can I do about that? Definitely, so it's like too naive view of the problem. So I can increase the dimensionality. So in some cases, we saw that, for instance, an ion permeating a synthetic channel just going along the long axis was not enough because I was stuck, when the ion was stuck, like chelating the NH groups. The chloride ion was chelating the NH groups. If you take a sodium, it would be the same, that it would be chelating the CO groups of the channel. And the binding, unbinding corresponds to this orthogonal high free energy barrier. The unbinding would be like 5 kcal/mol, 7 kcal/mol. So to rip it apart and allow it to diffuse, right? So in that case, we kind of solve the problem by adding a radial component to the reaction coordinate model, and that already kind of helps. There is this approach here that I have to mention because it exists. I mean, it's not coded in NAMD, but I mean there was a promise by the author to have it in NAMD. I'm not sure when it will happen. Don't laugh in the back. Don't laugh. He said it. He said he won't do it. So have some confidence in the man. So random walk in orthogonal space. So means that you're not just you're actually doing a two-dimensional potential manifold. So you're not just sampling in the direction of psi. You're also sampling in the direction along the derivative. Then you can change your importance sampling algorithm. And you'll see that some algorithms are a little bit better. Actually, even turning from ABF to extended Lagrangian ABF helps. It so turns out that we observed that the fact that you add this fictitious particle kind of introduces some noise and helps somewhat. Or you can turn to really ergodic sampling. That's the beauty of range calculations. You can combine algorithms seamlessly. So you have your importance sampling algorithm, so variance reduction, PP, TI, whatever. And then you can, using replica exchange-based algorithm, definitely help ergodic sampling. And then improve the reaction coordinate model that's kind of related to the increase of the dimensionality. So returning to ABF, so we already talked about it. And,
yes. Just a question about the previous slide.
Yes.
So it's not clear to me, like, how just by changing the importance sampling algorithm you can fix that problem, because unless you increase dimensionality or change reaction coordinate model,
Yeah.
even if you just change the importance sampling algorithm, you are still stuck.
I'll give you an example that I hope will convince you.
Okay.
I'm not sure that I'll be able to explain to you why it works better.
Okay.
But we have examples where actually it does improve things. And by that, please do not construe. I've said it. Giacomo said it yesterday. There is no universal algorithm out there, importance sampling algorithm that will solve all your problems. It's fooling yourself, believing that one method is so much better than all the others. That's not true. Because they all suffer from the same problems, essentially. So what you see here is ABF in action, right? I mean, ABF reconstructing the two-dimensional potential mean force for dialanine or decalanine, right? And so you've seen this. I mean, I explained to you the other. I should have shown you this little schematic here. Basically, we are accruing samples in every bin, and when we reach the threshold, then we apply the average force. But as we've seen in this movie, if you apply the bias too fast, the threshold, the value of full samples, is too low. Then we kind of overshooting the potential of mean force, and we're basically driven out of equilibrium. Then we have to spend some time to kind of heal and then recover the equilibrium potential mean force. So one way to address the problem, as I said, is to increase the dimensionality. This is something that we actually worked on with Giacomo and Jerome a few years ago, 7 years ago. We noticed that when you do the potential of mean force for decalanine in this safe region, that's what we have in the tutorial, going from 12 to 32, then well, it's easy to nail down the alpha helical state. But then when we increase the range of value, we go down to class 4. Then we are in the high compact region for the peptide. And then the reaction coordinate model, the simple end-to-end distance, is not enough to discriminate between in a haystack of highly compact structures. And actually that was obtained in a 500 nanosecond simulation, and we lost track completely of the alpha helical state. We were not able to, at some point, kind of disappeared. We are lost, and we're not able to recover the alpha helical state. And so one approach was to go to increase the dimensionality of the problem, to replace the end-to-end distance by 3 RMSDs with respect to typical conformations that we are sampling in the course of our simulation. So the 310 helix, an alpha helix, and a conformation that we call omega that we saw a lot of this conformation. And so if you do that, then so you have this nice 3-dimensional energy landscape, and then we are able to recover here the alpha helical state, which according to this graph corresponds to the lowest energy state. So one approach that one important sampling approach that we introduced a few years ago with Tony Leviev is a generalized adaptive biasing force, which is kind of a 4-man multidimensional energy calculation. So instead of doing a true multidimensional energy calculation, we're doing instead of doing like an n-dimensional energy calculation, we're doing n times a 1-dimensional energy calculation. We're getting, and from that we're getting the marginals. Okay, so in the different, and we a cheap recovery of the two-dimensional potential of mean force, or the two-dimensional histogram, which of course doesn't include the coupling terms, which with a different degree of freedom. But as you can see here, in the case of dialanine, so this is what we obtained, and this is a true two-dimensional potential of mean force. It's dialanine in water. And as you can see, I mean, this is pretty similar. It may be fortuitous. Actually, we saw that it was quite fortuitous. Going back to the synthetic channel with the chloride ion diffusing in it, we're not able to reproduce the correct potential of mean force. But what we did is we used that as a tool to bootstrap a real multidimensional fringe calculation. So we did a generalized adaptive biasing force calculation in along the long axis and along the radial direction separately to get the marginals. We reconstructed the potential of mean force, the pseudo potential of mean force, and used that as a starting point of a real two-dimensional fringe calculation. And that really accelerates it. I mean, that kind of saved us time, factor of 3. So I was saying that the extended biasing force, I was saying that the other day, that extended biasing force can be used to address limitations of the adaptive biasing force. A lot of these limitations no longer exist because, I mean, this has been fixed in the latest Colvar's version. I mean, one of the limitations was the impossibility to couple the reaction coordinate model with atoms that are involved in constrained bond lengths. Constrained forces would contaminate the measure of the thermodynamic force along the reaction coordinate. So that has been fixed. But you still have one limitation, which is the independence of the coarse variables, which should be orthogonal. And so if you use the extended adaptive biasing force, you can actually address that this problem. And so, for instance, in this case, with the reaction coordinate model, so we study the isomerization of cyclohexane going from the boat to the chair, and the reaction coordinate model that we chose was the sum of 3 torsional angles. That's typically something that you can do with ABF, short ABF, that you can do with EABF, and that kind of works nicely. So then we have combined extended biasing force with generalized biasing force. And so what you see here is the phrenology map for dialanine in water. And we studied that with 4 methods. So ABF, generalized ABF, extended ABF, and extended generalized ABF. And our point of reference is a long 200 nanosecond multidimensional ABF fringe calculation. And we calculate the RMSD of the gradients of the map with respect to this reference. And as you can see, EGABF is kind of the fastest to get you close to the reference map. I will pass that. So another class of approach is non-equilibrium work experiment in the Monte Carlo propagator. This is something quite recent, actually. It's not yet even published. It's under review, but it's based on an algorithm that has been published by Chen Wu in 2015. And that kind of relies on the non-equilibrium switches. So in this case, in this particular case, we run equilibrium MD, and then we ramp up through non-equilibrium MD. We ramp up to another Hamiltonian, and then we ramp down. We do the usual Monte Carlo Metropolis Hastings criterion for acceptance rejection. What we do actually, when we ramp up, we're changing the propagator. So we have like a classical MD propagator. And then to accelerate sampling, we turn to a different propagator. So in this case, we turn into accelerated MD for a brief period. So we hope that using accelerated MD will bring us to a different area of phase space, and then we'll ramp down. And that you can combine with, you can do AMD with adaptive biasing force with Urbana sampling. Yes?
When you say accelerated MD, you apply a boost to...
You apply boost to the torsional angles.
So how do you, like, how do you decide what boost to?
You mean the parameters? That's the parameters of AMD?
Do you have a value of boost like 0.2 or 0.3 that you apply to the whole torsion energy?
Yeah.
So like,
well, what we've done, we do some preliminary simulations of, like pure AMD simulations, see what's the best boost.
okay.
And so what we do is we run a certain number of steps of equilibrium MD, then we go up to turn to AMD, run AMD for a while, and then go back to equilibrium. But the parameters are optimized from like preliminary simulation, pure AMD simulation. So if you do that, then you can really accelerate things. So in this case, we were again revisiting decaalanine and over the entire range and comparing with pure ABF. The reference free energy calculation is multiple Walker ABF. I'm going to say that for the minute. Multiple Walker ABF. So we're pretty sure that this is a converged simulation, 8 microsecond simulation. And definitely, I mean, if you compare, so you have like in red, you have the ABF hybrid, so ABF is accelerated ME, pure ABF. Definitely in terms of uncertainty, we're doing a much better job with the hybrid method. So I was mentioning the multiple Walker ABF. So when you do ABF, I mean standard ABF, so this is the typical commands that you put in the call bars file. So when you have this double well, this kind of bi-channel case that I was mentioning, with one Walker, you're usually unable to cross the barrier. And so the hope is when you do multiple Walker ABF, so you're basically spawning your Walker according to the number of nodes that you have available. And so each Walker lives its kind of happy life. And every so often, so that's the shared frequency, so every 2,000 steps, they exchange information on the gradients that they are seeing. So this is done by, you just have to add shared for shared ABF, for multiple Walker ABF, and the frequency at which you want to exchange information. And then in your landy config file, you introduce the keywords myReplica. So for the coordinates, for the velocities. So it's kind of advisable to start the simulation with different points of the conformational space that you've obtained from preliminary equilibrium simulation. And so by virtue of myReplica, so myReplica, blah, 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 myReplica.core vel XSC, then you can read different configuration to bootstrap your simulation. And so this is the same decaalanine problem that we've talked about, and definitely when you do shared ABF, we do improve things. A little bit of a disappointment. So there was this idea that we published in 2010 with Tony earlier, but the Sailor idea was with Tony in 2010, and Tony thought about like even improving the scheme with kind of Darwinian selection rules. So basically, you kill the slackers and you promote the good students. So in this case, I mean the workers that are kind of stuck, don't do much over a certain period of time. You just and then you promote, you clone the good workers. But somehow it hasn't been very. We haven't been very lucky with that. It should have worked better. Should I? Well, I'm sure that Wei will go into the detail of that, but just to finish. So in the case of energy perturbation calculation, you can also use this replica exchange framework. And so this is the idea of Hamiltonian hopping. So in Hamiltonian hopping, you're basically exchanging lambda states. So remember you're doing your free energy perturbation. So in this case, we are interested in the hydration free energy of benzene. So we have our assay is a benzene molecule in a box of water. We're going to make that disappear. So as you go along lambda from 0 to 1, then it's progressively decoupled from the aqueous environment. So you clone that on the different processes that you have at your disposal, and then you propose some exchange, some swapping between lambda states, and then you run, and then you decide to accept or reject according to the energy of the box with respect to the different lambda states, just like in a regular replica exchange approach. And so then of course, when you accept, then good. If not, then you swap back the boxes. We do that. We select randomly the box or two adjacent boxes. We don't do that. We don't take this box and that box. We take like adjacent boxes. Now, if you remember what I was saying on the first day about entropy calculation, one way to access entropy is to use these finite differences. I was mentioning the work of Ron Levy. So basically, we calculate the derivative of the free energy with respect to the temperature using finite differences, just small temperature increments. So what you can imagine doing is a two-dimensional replication. So you're not just cloning with the lambda states, but you're also cloning in the temperature space. So you're doing replica exchange in lambda space and in temperature space. Okay. So you're swapping in lambda space, but you're also swapping in temperature space. So you can do that like alternatively. Okay. But it's always the same idea. The same idea is to make high temperature configurations available to the ensemble at low temperature. So typically, when you have like a flexible solute, and remember the problem that I was mentioning, so precision versus accuracy. I'm trapped in one conformation, and as I decouple the solute from water, I'm trapped in one conformation. I'm not sampling the other state that nonetheless contributes to the free energy operation. Right? So in terms of precision, I'm doing good. In terms of accuracy, I'm doing bad. Right? It's very possible that with this kind of mechanism, you may give other state available. Right? Because it's very possible that when it's almost decoupled from the environment, then it's easier to isomerize. And then suddenly it becomes a variable here. Yeah.
So in this case, the lambda for each temperature should be same, right? It should be, if you are doing it.
Yeah. So the temperature is the same here, it's the same here, it's the same. But it's very possible that at some point, some of the contributions down there will go all the way up here after so many swaps, horizontal and vertical. Yeah?
What's the exchange criteria here for the energy? Like when you swap horizontally or vertically, you have different criteria?
You will have two criteria. You have the criteria in lambda space, and you have the criteria in temperature space.
And you don't check the energy on the other dimension when you decide to swap.
No, it's either you do one or the other. Usually you do it like, alternated. You do lambda space, you do temperature space, you do lambda space. And that's how we do it. That's it. Any other question? Yes?
So when you calculate the BMF, do you consider only one temperature or?
Work in progress. So we have like we will have sometime soon shared AVF with temperature exchange. I suspect it's already done. Actually, potentially it can be done with umbrella sampling. So with umbrella sampling, there is a bias exchange, which I'm sure that Mahmoud will talk about tomorrow. But you can combine it. Potentially, it's done, right? I mean, the thing is, that's the beauty of NAMD. We talked about that yesterday. A lot is available. And it's like, there's much to do to make it available, completely. But you would have to write like a few lines of TCL code to have it. But all the infrastructure is there to do bias exchange and temperature exchange. Yes?
Can we use this method now?
Is it available?
Yes, it's available.
Soon to be available. Wait. Can we use this method? It will be soon available.
Yeah.
And by soon, I mean like very soon. And if
Actually, we already have this method there, but just not there documented.
yes, it's not documented.
I will show those scripts, and also would like to listen to your opinion or suggestion, because last night we already talked with people. We immediately started writing a document for this method.
Yeah, we consider a method to be available to the public when it's nicely documented and if possible, comes with a tutorial. If it's not documented, then it's useless. So the scripts do exist, and they've been tested. Especially by weight, but it's not fully documented, and so therefore, it's like right now, I would discourage you to use it as is, but it will be soon, and the scripts will be improved so that when you can use them, just like the scripts that you've been using in the tutorial, you can use them in a kind of a transparent fashion. Okay. So you don't have to bang your head against the wall to try to figure out different options.